So I'm Mark Kerwin. I'm the lead technical sales engineer at Fractory. I specialise in sheet metal fabrication, and it's great to see all of you out here today who made it down. We've got people who do know about us a little bit more, but also some people who are new faces to Fractory might have seen us on social media. So I'll just give a quick overview of what we do here before delving into the presentation on bringing down the cost of sheet metal fabrication. So we're Fractory. We're a cloud-based procurement platform that works in automating all of your outsourcing needs from quotation through to delivery. So trying to save a little bit of time and price in the admin involved in that. What I'm going to be talking about in this presentation is more how to save money in sheet metal fabrication, so a little bit more focused on that, and hopefully you can take something from it for your next designs. So why is cost-effective design so important? When you are going through the initial design phase, so going through prototyping, there tends to be a lot of iterations. This can take up quite a lot of time, slows down actually getting your product out into the market. Typically, the reason these iterations come about can be through various reasons, such as consumer feedback saying you need to change a little bit in the aesthetics, or you have a new idea in how to make your product more effective, easier to use in the marketplace. But the absolute king of why iterations come about is always going to be the price, making sure you're most competitive in the market, most competitive against your competition for winning a project, and always going to be the most important factor in any design that you put across. So with that being said, when we're looking at the costs that are parts of your part, and say they're on the shelf and for retail, tends to be about 5% of the cost of the part on the shelf is from the actual product design itself and the investment you put into that. 20% in the material, 15% in labour, 30% of your overheads. These are quite generic values. They can be wildly different from product to product, but in essence, the product design phase of it and the actual cost of getting these designed up tends to be on the lower end. However, it does cast the biggest shadow onto the influence of the final price of the product. So decisions made at the very early stages can really ramp up the cost or save money in the final product on the shelf. Which is why it's so important at the early stages to think about ways to be saving money. I've broken down sheet metal fabrication into 5 stages. There is definitely a lot more complexities when you are fabricating sheet metal and going through production, but in essence, once you come up with your design, it will go to a production team. They'll then be programmed into the machinery. The metal will be cut, then bent and formed, then go on to welding and assembly, and finally surface treatments such as your painting, powder coating, anodizing, galvanizing, whatever you need to be able to, whatever your product needs. First thing that you'd be wanting to consider when starting to put your product into production is your material selection. So advice is obviously to research into what appropriate materials are for your application and making sure that that material has the right properties for what you're trying to produce, whether that's the yield strength, the ductility, or if it's going to be outside, you may need to make sure that it's corrosive resistant. Making sure that you have the right kind of material is always going to be important. In that research, try and get a range of materials that you could possibly select from, so that when you're going through quotation, you can get a more cheaper option and just try different things out. It's always good to ask the manufacturer that you're working with what they have on the shelf, what they typically stock, what the majority, say if you're wanting aluminium, what the majority of the aluminium work they do is, so they're common grade, because typically they'll be purchasing this in higher weights for other jobs, not just your own. So the cost per kilogram naturally would be lower than going for a more exotic grade that you've heard is out there, which they don't typically buy. Once you've decided what kind of material you're wanting, making sure that components in your assembly are pretty much the same thickness as other components in the assembly will mean that you'll be reducing the cost per section of material you'll be using. For instance, say if you were ordering 3mm aluminium, all of your components are made out of this. Due to unit economics, the cost of each of those parts will come down, rather than if you were using 3mm, 4mm here, 5mm here, where you're not really getting the most out of your material. Once you've selected your material, you then start looking to the actual sheets that are going to be used. Predominantly, these tend to come in sizes of 3m by 1.5 meter or 4m by 2 meter, usually governed by the size of the laser beds or the machinery beds that the manufacturer has. But they can go down to smaller as well, such as your 1.25s by 2,500. The reason I wanted to point this out is the more material you use of a certain sheet, the cheaper it tends to be, because you don't necessarily want to be paying for the wastage or leftover material on that. You might as well get the most bang for your buck. Now, looking into how that relates into practical, I've got a folded component design here. Looks like pretty standard, just with 4 folds on it. The reason why this is quite an interesting piece is because the actual sizes of it are 740mm across by 495mm down. Now, start going back to what I was talking about with the 3 by 1.5 meter sheets. This fits really nicely with fitting about 4, fits 4 across and 3 down, so that you absolutely maximize the sheet. You can get 12 of these components out of one sheet. If this was a little bit over, so 760 across by 505 vertically, you probably only actually fit 6 of these components on one sheet for the same amount of material. So really considering the size of the flat patterns and what you're going to be putting onto there and how they're going to nest is a large factor in bringing those material costs down, using the most of the sheets and not spending money on waste material. And now I want to just talk quickly about an example of a poor use for sheets. So this component can be seen as the channel in the middle and a few bent features around the outside. When it's translated onto one of these smaller sheets, so a 1.25 by a 2.5, we can see that the sheet isn't used properly. You've got big gaps in the middle, which inevitably you'll be able to pay for, because the manufacturer is not going to necessarily use these gaps in the middle for the future jobs, and you're going to be really uneconomical on how many pieces you can get out of the sheet. What was done with this particular part was the lighter grey bent flanges were actually removed to be welded on later, so they were cut separately, and rather than having 3 of these channels on a sheet, 4 of them were able to be put onto there. The bent flanges, the flat pieces, will also be able to nest it around here, so rather than having 3 of these components on one, you were able to have 4. Now, on a smaller order, that might not make too much of a difference, but if you were ordering these in the hundreds, you're basically getting 1 free in material for every 4 that you're ordering, just by being able to do this. Now, another factor onto if this was in a smaller one, the actual cost of setting up the welding for putting these on might mean that you're not really saving too much. But again, on larger projects where you are making higher volume of these, you will be saving a fair bit of money just by getting 4 onto the sheet rather than 3. But it's always something to consider when you are doing your designs. Now, minimising the cost of cutting. So once you've decided on your material, your design, how that's going to be fitting onto a sheet, you want to then start thinking about your cutting methods and how you can potentially save money in here. Now, I've got a few of the cutting methods just up on board here. I'll just run quickly through each one. So we have the guillotine, which is great for cutting basic geometric features or halving a sheet and you want some smaller sizes for yourself. It's quite simple and it typically over those thinner gauges of materials won't give you those intricate pieces which quite a lot of sheet metal fabrication is, but it is a good option if you have a basic geometry to your piece. The punches, as you can see in the middle image here, that's custom tooling which punches through the sheet metal to actually cut out features such as squares in this image, but also for holes or anything you want really, as long as you can stomach the cost of setting up getting the tooling made in the first place. So with that being said, again, not really too practical for your smaller production runs, but when you've got higher volume, it does come into play and really does save time. Also on top of that, it's very accurate and repeatable for every single feature that it punches out, because it will always be just what the tooling actually is. That punches it. It can get through large volumes very quickly and could save money in the long run, particularly after you've done that first time investment. Then we start looking at more of the thermal cutting processes. I've put in brackets some of the prices per hour. Now, the reason why there's quite a large fluctuation in these and quite a large range is because it can just change dependent on the job, dependent on how thick the material is that you're cutting, dependent on the volume of the work itself. So it is hard to pinpoint the exact cost per hour, also due to the actual machinery you've got. You might have a really high-powered machine or a low-powered machine. But I wanted to keep these ranges in just so you can kind of see and kind of stack them up against each other for your own jobs. We have flame and oxy cutting. Flame cutting uses they're pretty much the same, just a slight difference. Flame cutting uses air with a fuel to produce a high temperature flame which melts and cuts through the metal. Oxy cutting is very similar but uses pure oxygen to make a much higher temperature flame, cuts through the material quicker. This is typically for your thicker grains. It does tend to be the cheaper option, but can leave quite a rough cut edge. So typically you might have to do additional work onto this after they've been delivered to you or before they go on to the next stage. So always consider that as well into when you're trying to save some money. Going on to plasma cutting. This is a high velocity ion beam. It also just cuts through and melts the metal. This can be on thicker and thinner gauges as well. It's slightly smoother cut quality than your flame and your oxy. You might not need to do work afterwards, or you might need to. Typically, it's good to get some samples cut off on plasma before you start going ahead with some of your larger projects, just to make sure that that can be right for you. The next thermal cutting is laser. This is typically for your thinner gauges. It's a energy beam which is intensified by computer-controlled mirrors. It gives a very precise and smooth cut, typically on the thinner gauge materials. It tends to be more commonly used in sheet metal fabrication just because of the higher precision of the cuts for relatively good price and the cut quality itself. Interestingly, quite a lot of jobs that I do see that actually come through which are in laser could probably be switched down to plasma, just because they could probably accept a little bit of a lack in cut quality, particularly for parts which might not be custom facing. So internal components which are just that little bit thicker, or if you work in an industry such as the sewage industry, for instance, where you don't necessarily really care too much about how those cuts look, you just want a piece of metal cutting to fit a purpose, then you might as well cut down and save yourself some money there. The final cut I just want to talk about is water jet cutting. This is the most expensive of the options. It uses a high pressure water jet. with abrasives mixed in to just part the material. It gives a very, very fine cut quality finish. It has very fine tolerances, finer than laser, and because it's not thermal, you can cut smaller details into a metal part without worrying about warping, bowing, and can just create those more precise features. So figuring out which one of these you want to go with and what you want to have on your project can have a large effect on the overall cost of the job itself. Now, I do see quite a few people coming in and are asking for water jets again when they can probably accept plasma just because they've heard water jet is the best. You don't necessarily need to buy a Lamborghini when a Ford Focus will do. So really considering actually what the application of your parts are is always going to be important here. Now, just looking at some of the limitations with these, I was already talking briefly about thicknesses that they can cut. You can see that laser, so I'm just going to take mild steel for example. So the laser tends to tap out at around 20 mil of thickness. Now that is kind of in general for a lot of lasers out on the market. There are now lasers which boast cutting up to 30 mil. So for this, definitely speak with your manufacturing partner that you're working with. Really understand the ranges of their machinery, and you can make an informed decision on what you're wanting to work with. But for instance, if you have 15 mil thick mild steel, you can have them cut by laser, plasma, or water jets. And it's just considering those tolerances, the precision of the parts you need, and the quality of the finish that you need. Talking a little bit more on the actual cut quality, you'll find that cuts are very rarely going to be completely perpendicular when they come down to the surface finish. There's always going to be a little bit of an angular deviation, and that will be increasing as you go up in the thicknesses of material. So you can see even for water jets on the thinner gauges, it's pretty much negligible, that chamfer, the deviation. As you go up to some of the higher thicknesses, such as 35 and 40 mil on this chart, you'll see that starting to push out. After water jet comes laser, then your oxy-fuel flame cutting, and then your plasma. This could have implications onto your design if you're wanting two ends of a part to meet up, to be welded together, as you may need to rework and grind them down so you've got that nice perpendicular edge to push them against each other rather than pushing out from each other. Now, we're moving more onto the folding now, so that was the cutting. We at Fractory actually have a bending calculator on the back there. There are some little card pieces which have all of this information on. You can slide them across to a given thickness you want. It will recommend bend tooling for yourself. I'll just talk through it briefly. Press brake has this blade which comes down. This has a radius at the end. That's the bit which touches down onto your workpiece, which would be resting horizontally across what we call the V-die at the bottom. The blade pushing the material into the V-die is what causes the actual bending, gives you your angle, and also gives you your radius internally inside that bend. So for a given thickness, these typically will be the toolings that we'll be recommending. Our calculator will show you the V, so the V-die that we've typically used, the internal radius of that bend, which you'll include into your design, and the force that will come down onto the actual material for using that radius. That can then be iterative back up to the material to make sure your material doesn't crack. And the most important feature on this calculator is this V dimension. This shows the minimum length that the flange can be for it to be able to sit right on that V-die and not slip when the bend does come down. Consequently, going back to design phase, try not to have any holes within this distance, as that's where the material does start to bend around, does start to stretch, so it can cause an elliptical feature rather than a hole. So you might find that you'll need to drill out those holes again after you've received the components. Again, just adding to a cost, having to redo a prototype, and just adding a time where it doesn't necessarily need to be added if you can just factor that into your design. When you're looking to reduce the cost of folding, my best advice tends to be making sure that the press brake operator doesn't have to change out the tooling constantly across your parts. So it doesn't have to change that blade or change the V-die. So when you are carrying out your design, making sure that you have just consistent bend rads throughout the whole design means that every single one of these can be knocked up. Just knocked out without the press brake operator having to do these changes, wind the machine down, and then start up again. At the back of press brake, there'll always be a backstop, which is where the material pushes against. It makes the material at the right place for the blade to come down and carry out that fold. When you've got quite a lot of tabs on a part, making sure that they're the same distance from the bend line, so that that doesn't have to be reprogrammed and moved as well, is another way to cut down on setup costs and save yourself some money, and save yourself some lead time as well, getting parts out quicker to you. Now, I've got a couple of examples of folded components, and where typically we try to save some money and reduce some costs. We've got this lovely piece here, which has tabs all the way around the bottom. That's the same on the other end, and this kind of conical form feature, which is made up of lots of bends, which we call step bends, just to be able to give that larger rad and larger angle. Now, when this is flattened out, you can see that all of these are kind of at a different angle to each other, meaning that if the press brake operator is to work with backstops, he needs to try and offset them. It takes quite a lot of skill, quite a lot of knowledge, and a lot of time to work out how to do it and make sure that it's right. This could have quite high cost implications, as opposed to the tabs that go around the outside, all at the same bend rad, the same flange length. Simply, we're seeing this as nearly 2 meters in length, probably 2 people just stood around, just folding each one and moving around the piece, making it nice and simple. So what we recommended for this particular job was actually taking away some of the precision from the folding. And on this flat pattern, when it was on the laser, we etched the lines for all of these folds onto it to be able to give them the placements. And the press brake operator literally lined these up by eye over the V-die for where the blade would come down. I believe this, due to the skill of the operator, this was about a plus or minus 1 mil tolerance, but it meant that these could just be radically ramped up in how many could be produced per hour, bringing down the cost of them. Now, that being said, not everyone would be able to accept the push out in tolerance, but if you're able to factor it into your design, you can start saving money just by not having them as precise as possible. Obviously, talking with your manufacturer, working your way through that is the best course of action for these more complex parts. The next design we have is for small brackets, which have been made in the tens of thousands. Now, these brackets, they were originally all just as one piece. Each one has 2 folds on either end and 3 tap tollers. We needed to be able to get these produced at very quick speeds for the clients, and what was proposed was actually tagging these all into each other to turn these 10 brackets into just one piece that comes off the laser. What that means is each one of these pieces, when it goes to the press brake, rather than being folded individually, you'll do one, then the other, and do that 10,000 times, you were able to hit 10 of these pieces at once to create the folds, literally reducing the time at the press brake by 10. As you can imagine, that has a huge implication on the cost, as well as how quick you can get your parts, get them moving. The only limitation on doing something like this, however, is when you're snapping the pieces off to make them back to those single brackets. Fortunately, these were internal components, But what's usually left behind is a little bit of metal in here and here on the piece, a little pip. For these pieces, it was about 1 to 1.5 mil, depending upon the piece, that was left behind. As it was internal components, it didn't matter too much. For external components or aesthetic, it might matter. But again, talk to your manufacturer about ideas to be able to reduce folding. But if we were to start removing those pips, you'd probably be spending the money that you just saved in doing the folding. So it isn't for every application, but it is definitely one to consider. Now, coming on to actually more towards assembly and designing your assembly and main components, and it's going into simplifying the design. You might not be able to see from where you are, but every single one of these pieces is unique, and there were quite a few of these different assemblies, all of them unique as well. Slight changes. This piece is slightly bigger than this piece, which is slightly bigger than this piece. Same with the flange lengths, bends in every component in there, making them really time consuming, just even that programming, making sure every single piece is nested up onto the sheet. And once we go to folding, they have to come off the laser in a particular order so that it matches the press brake operator's massive pile of PDFs, which is unique for every single one of these pieces. And he's got to make sure that he's folding them all correct. Then you go over to quality assurance, who have an absolute nightmare of trying to assure every single one of these components is right. Lots of measurements, errors happen, parts have to be returned, remade. Lots of added time to this job just by having all of them being very unique. So when you are designing an assembly, trying to use common parts as much as possible. As Tom was saying with the fan housing, all four sides were all the same piece, makes it a lot easier for quality assurance, brings the time of actual production down, everyone knows where they stand with every single piece. There's not too much thinking needed to be done just to knock them out and get them correct. And also, by doing that, you reduce the setup and make a speedier and more reliable QA process. Interestingly enough, the same client who's working on this project has come in with a new framework where they've replaced sheet metal with box sections to give the internal framework of the piece. As you can see, it's a lot simpler, a lot more common pieces in there. And as they switch to box section, it's nice and simple. It's just cutting the ends of the tube, putting some holes in. As they're similar, QA process is a lot more sped up. You can literally see that all of the pieces are the same as each other. Put them next to a PDF, just get some measurements for one of them and know that they're going to be going through fine. Once you've designed your assembly, obviously you've got to choose about what kind of way you're going to be assembling it. One of the more recent technologies which is coming up and becoming more and more popular is robotic welding. So robotic welding is intrinsically more efficient than manual welding. They make less mistakes. I'd love to say they make no mistakes. I've personally never seen one, but just in manufacturing, I don't like to say makes none. But it greatly reduces the labour costs involved in welding. They run 24 hours a day, don't need to take lunch breaks, no cigarette breaks, and can just knock out your parts a lot quicker. This is really good for large-scale production runs of assemblies, just because to actually get these set up and programmed, you need a highly skilled technician with a lot of knowledge in welding to make sure that these are programmed to do exactly what they need to do to create the product. So if you've got a one-off design, it's probably not going to be that cost effective, but if you've got thousands of the same assembly going through, you're really going to be saving some money and getting your parts a lot quicker than if going through manual shift labour. Interestingly enough, just to add to that point, in two major manufacturing industries, the automobile industry is, you may remember car ads probably about 10 years ago where the cars were going down the production line and all the robots were building them up. The automobile industry uses these 80% of the time for their production. There are 5,000 weld points in there but it's the same every single time, onto the next job, onto the next job. And for 24 hours a day, they can be producing cars. Whereas for ship construction, it's a large one-off project. To actually set up a robot welder in every single segment with every single nuance and new aspect of the job of shipbuilding just wouldn't make logical sense. So even though this is also a very large project, that would use manual welding for 80% of the time. So when it does come to welding, really consider your job, speak to your production team, see if robotic welders would save you some costs. But typically for one-off bespoke components, manual, for lots of parts, look to some robotic welders. One of my favourite words that I came across in engineering is the idea of poke yoke when it comes to welding. So the poke yoke is a very simple concept. You've got a tab on one piece, you've got an open slot on the other one. And these slot together prior to welding, and it just makes sure that the placement is all correct without the use of jigs, which also would have to be priced for. It means that the welders can move through your project a lot quicker, saving yourself time, and just gives you a lot more confidence and control over the quality of your own product whilst it's on the shop floor. One thing to note here, if you are going to design, however, is to make sure that the slot is slightly oversized, just because of the tolerances on, say, if you're having these laser cuts, it could be on the minus side, meaning that it might be a bit undersized and not quite fit, which could be a bit of a nightmare. So speak with your production team at what size that needs to be, just to make sure that it will work for you. But you will save substantial amounts of time. In fact, I've brought some brackets down that do have the poke yoke design just here. Feel free to have a look yourselves. And interestingly enough, these were both robot welded as well. So if you want to have a look at what kind of quality you can get from a robot, these should give you a bit of an insight. Now, one thing which I've been saying throughout every single section during manufacturing is talk to your manufacturers to help with your cost-effective design. If you're talking in the initial design stage with them, it should minimize failed prototypes, failed designs where you might have been able to get a cheaper option, use a cheaper material than the one you've had produced. It just cuts down those iterations, gets your product onto market quicker, and you can start making money, or you can start solving your client's issue quicker. And also use their experience. They work day in and day out with the machinery on their shop floor. They know the quicker ways to get around it, the cheaper methods to do it, what you can kind of push out a bit on tolerances, what you might need to tighten up, and just tips and tricks into how you design your piece to save yourself some money. So just as a quick summary, use the full sheet. Can you optimize a cheaper cutting method? Think of the actual people who are going to be making the parts, what labor they're going to have to go through, and try and visualize if there are maybe quicker ways that they can do it, and talk to the actual manufacturer that you're planning on working with to try and save some costs. Well, if you think of anything after this, feel free to drop me an email, drop me a call. I'm more than happy to talk through anything with yourselves. Thanks for listening.